I'm going to talk not so much about the astrophysics, though a bit of that will come into it. But remembering that we're a science and technology society, I thought I'd have a focus on the technology of how some of this stuff is done, because you simply very rarely hear it talked about. And when I was a young research student at the Cavendish laboratory, I regularly used to take people on tours around the radio telescopes at our observatory. And after about 2 hours talking, we'd get to the end and give them a cup of tea, and I'd ask for questions, and inevitably the same question came up every time: where is the eyepiece? And of course, there isn't an eyepiece. So this is a very belated attempt to try to explain why radio telescopes don't have eyepieces. But nevertheless, we can actually form images. And trying to explain the technology of radio astronomy, it's subject, you might as well ask an organic chemist to explain the technology of organic chemistry. It's an enormous subject. So I'm just going to focus on one area, and taking as my task an attempt to try to explain how you produce an image of a black hole event horizon. And it's actually an enormous technical achievement. And if you actually go to the Event Horizon Telescope website, you can get an explanation for the general public, which honestly might as well say it's done by magic. And the explanation for the professional astronomers basically requires a degree in theoretical physics. So I'm going to try to pitch an explanation somewhere between those two extremes. And what I also want to point out is some very surprising connections between the technology which is used to produce images like that and things you're very familiar with in everyday life. That will come later in the talk, because there's been quite a lot of spin-off from radio telescope technology, and it's in your homes. So the other thing we'll come along to is, again, very surprising connection. When I was a young astronomer, we were told we'd never be able to image the surface of a star. You know, they were just too small, too far away. But here we are, this is an image of the surface of a red giant star. And the interesting thing about this is it's produced with exactly the same technology that was developed basically in the middle of the last century, by a lot of it by Martin Ryle at the Cavendish laboratory, but has now been converted into optical frequencies, which is, again, is an astonishing achievement. Now, I can't, obviously in this time, I'm not intending to run through my entire talk here, but that's the basic thrust of what I'm trying to get at, is how the technology has changed quite astonishingly over the past 40 or 50 years. And one of the things I want to try to explain is something Martin Ryle always emphasized, is that what we could do with radio telescopes was always limited by the available computing power. You know, it determined the size of the telescope you could build, the number of dishes you could accommodate, the rate at which you could do observations. It was the big constraint, even to the current day, is the computing technology. And that image of the black hole only became possible because of the vast increase in computing power, and particularly data storage capability that's happened in the past decade. So I'm just going to flip through some of these screens fairly quickly, because what I want to do in this bit is really just to test out the bits of the presentation which, if you like, require a bit more technology, like animations. So yes, the first bit of the talk really is the basic landscape, where radio waves are, how we've got an available window through the Earth's atmosphere, and the basic history, which started before the Second World War. And of course, what happened then is all these guys became radar experts in the Second World War, and they came out of the Second World War with a number of, it had changed them in a number of important ways. First of all, they could roll up to military establishments with lorries, and they just give them truckloads of electronic equipment that the military had no further use for. And also one very important thing is all these guys were now, they were very young, they were very aware, they had taken enormous responsibilities, and they were used to working in teams and accomplishing remarkably difficult projects in breakneck speed, you know, and it was a real social change in astronomy. And for a long time, radio astronomers were regarded as a strange, different breed by the optical astronomers who tended to work on their own. So we got the first observations. I'll say more about this in the physics of this in the actual talk. And the basic problem of radio astronomy is dishes like Jodrell Bank can't see much detail. They've got a very wide beam, so you can't see much detail. And not many big bit dishes have ever been built, in fact, because they're very, very expensive. And the size of Jodrell and the size of these is about the real practical limit for building a single dish telescope. And the other problem we have in radio astronomy is the electronics. Everything is a bit warm, and the electronics generates noise. So you're always battling with the difference between all the noise generated in the electronics and the very, very slightly larger amount of noise coming in through the aerial. So a lot of the early history is about how you distinguish between sky noise and electronic noise. So I'll explain that there. And how we produce electromagnetic radiation, the things that produce it, including particularly what we now generally call non-thermal radiation, synchrotron radiation. And the big thing that radio astronomy discovered after the Second World War was most radio emission is coming from between the stars. So what we're actually looking at here is a pattern of high energy particles and magnetic fields between the stars in the galaxy. And so this was, radio astronomy absolutely changed the view of the universe from a very static, graceful universe where not much happened to, in the 1960s, suddenly it was the violent universe. And some of you as old as me might remember television programs called The Violent Universe by Nigel Calder. So what we needed to do in radio astronomy is get much, much finer detail. And the way to do that, which was really the specialism of the Cavendish Laboratory, Martin Rao's group at the Cavendish Laboratory, they became virtuosos of using a technique called interferometry. So this is my first animation, which is trying to explain how, you know, radio waves coming in, being received at two different dishes, and you bring the signals together, and when the full path length is at some directions you get coherent adding up, and others you don't get any signal at all. And that actually allows us to see some detail in the radio source. And there is a complication, which I'm not going to explain now, but I will in more detail in the talk, about the fact that real radio receivers actually receive a range of frequencies, which means that your simple ideas of interferometry don't work. And this was one of the big tricks that Martin Ryle invented, which suddenly made interferometry work. So I'll go on. So what we're looking at now is these fringes, a pattern where we can see radio sources, where we see those purple lobes on the sky, and in between them we don't see it. So you get, when you actually look at the output of the radio telescope, as the source drifts across the beam as the Earth rotates, you see what we call fringes on your pen recorder. And we have an extended radio source up there, but the lobes are wider than the source. But if we move the areoles apart, we actually move the fringes closer together, and the fringes disappear because some bits of the source are in the beam and some bits are outside the fringe. And that was how, in the 1950s, people began to understand the angular structure of radio sources. Very, very crude. Later on, we needed to do this source tracking, this extended source tracking. And why do we want to do that? Well, because the Earth is rotating. So the fringes are actually moving round, and we can get some idea of the structure of the radio source in different directions. Okay, I'm going to then explain a bit about Fourier synthesis. Too complicated to do now, but we can do it in 2 dimensions. And it turns out that interferometers are the way to extract the Fourier components of the brightness distribution on the sky. And we can then use a computer to add everything up to recreate an image on the sky. Now that will actually require a lot more explanation on the night, but this is the fundamental trick which radio astronomy now uses, and it's absolutely dominant today, the idea that you can actually observe Fourier components and add them up in a computer. And it was only the development of something called the fast Fourier transform in the mid-1960s which made all this possible. So it was a mathematical breakthrough which actually made this possible, because even before that point, well, I came across one detail when I was researching this. You could do 4 minutes worth of observation. It took 15 hours to invert the Fourier transform in a computer at that time until this algorithm came along. So it's about building virtual telescopes with diameters measured in kilometers. And this is the 1 mile telescope, the really big breakthrough which Martin Ryle constructed. And when I was a young research student, I sat at that control desk and operated this telescope. And when you're 21 years old, it's very crude by modern technology standards, but when you're 21 years old, it felt like driving Starship Enterprise. So it was a great experience. And we produced the first radio maps of some of these strange extragalactic radio sources, which have these 2 blobs of emission either side of a galaxy in the middle. And everybody got in the act then. This is a Dutch radio telescope which started to use the same techniques. Once Martin Ryle had showed how it could be done, everybody wanted to do it. Then Martin Ryle built another bigger telescope, and this was the first telescope which had better resolution than optical telescopes. We could see more detail than optical telescopes. And my PhD was based on data from this telescope, and it had been commissioned for a year, just coming into full production. So you can imagine a young research student, you come into this group and you are handed the very best data available to anybody in the world. So, you know, that was a fantastic experience. And so we started to produce really detailed maps of the sky with, and began to understand what was going on. And we had very strong suspicions at that point that there were supermassive black holes down in the middle of these galaxies. So my PhD was about generating evidence to support those ideas. The Americans eventually got in on the act. They could have built this 10 years earlier, but they were, you know, the American political system and funding system. There were 10 years of arguments about where they should build this and who should build it and whether it's going to be a university or a national facility, you know, typical American stuff. But once it was in production, it blew everything else away. It's by far the world's most productive astronomical observatory today, and produced fantastic images like this. And that's something I worked on as a research student. See a galaxy in the middle, these strange lobes on either side. And what you could see, particularly in this image, you see that line connecting that dot in the middle to those lobes on the outside. We began to understand at this point that there was a hypersonic jet emerging from the middle of that galaxy and blasting its way out either side of the galaxy. This is 500,000 light years across, okay? And this jet is material moving at very nearly the speed of light. So absolutely stupendous amounts of energy involved here. You could turn 10 million stars like the sun into pure energy, you know, E equals mc squared. That's what you need to actually fill these lobes up. You need to turn one solar mass each year into energy in order to keep this thing powered up. So that's the point at where, having done these calculations, we realized something really, really weird was happening down in the middle of the galaxy. You know, had to be some sort of black hole type phenomena. You can even see some of these things in the optical. So strange jet emerging from a galaxy known as Messier 87. So to get even more detail, we wanted to do very long baseline interferometry. Now there's a lot of technical problems here, which I'll talk about in a little bit more detail in the talk, because some of the tricks we used in things like the Cambridge 5 kilometer and the very large array can't be used here, because all these dishes are looking through different amounts of atmosphere. But one of the things that was developed as computing power came along, it was found that if you had, say, 30 dishes and maybe 60 or 70 baselines, you could do a lot of back calculation. You could observe a point source and you could work out exactly where all these dishes were to millimeter accuracy. And you could work out any time delays caused by looking through different depths of atmosphere. And eventually then you would turn that round and use it to calculate the image of the radio source you were looking at. And this time you're looking at thousands of arc-second resolution. So on the right, we see something which was measured in an early radio telescope, all surrounding a galaxy, and then we're looking at finer and finer resolution till finally down at the bottom left-hand side, we're looking very, very close to the center of the galaxy. And even at the smallest scales here, there are still unresolved things going on. So this is the incentive for this so-called Event Horizon Telescope, to really start to see what's going on right down in the middle. Now, one of the side effects of all this turns out to be, as I said, in order to make this work at all, we need to know the positions of all these aerials to millimeter accuracy. And in fact, we got to use the radio calibrations to deduce their positions. So this turns out, in fact, to be the very best way of measuring continental drift. And in fact, your Earth-based coordinate system, the geographical coordinate system, is now tied to the astronomical coordinate system by very long baseline interferometry. So when you get your mobile phone out and check out Google Maps, you're actually relying on this network of radio telescopes which continuously measure the positions of the continents as a side effect of their real job, and tie down the geographical coordinate system. So, as I said, even when we go to the very finest resolution observations with conventional very long baseline interferometry, we still can't quite see what's going on down in the middle. But we think it's something like this: a black hole and stuff is getting sucked into it, and it spins around in a disk, and there's some very complicated physics, not completely understood, which is generating jets on either side of the accretion disk. There's a lot of evidence now that astrophysics seems to find it quite easy to make these jets because they turn up in all sorts of situations, but we don't understand exactly how. You know, some very complicated computer simulations have been done, and they're sort of pretty, you know, we got a fairly reasonable clue. It must be something like this, but the actual details are too complicated at the moment. So that's why we need to image what's really going on down, really down there in the middle. And what you had to do with this, instead of 1,000th of a second of an arc, you had to use 1,000,000th of a second of an arc resolution. So they had to build telescopes which worked at millimeter wavelength. So they got many more wavelengths between the dishes. And they also had to measure the positions of all these telescopes taking part to sub-millimeter accuracy. Basically, you need to measure the positions to about 1/20th of the wavelength you're working at. Okay, and then you need to record the signals coming out of the telescope, timestamp them with atomic clocks, record them. Because you can't connect them with hardware, what they had to do here is record them on a pallet-high stack of hard disks. You know, it was petabytes, thousands of terabytes of data. And then they had to ship them all, and they had to play all these recordings of the output from the radio receivers on the aerials into a receiver in one central location, and spend a couple of years trying to make it all work and analyze it. So that's the fundamental basis of the technology that went into producing this. And it's absolutely extraordinary that they managed to do it. When you think of the accuracy with which, the precision with which absolutely everything had to be done. So where do you go from here? Well, here's a telescope which is now in full production in Chile. This is a synthesis telescope which works at millimeter wavelengths. Why do we want to do that? Well, first of all, for resolution. Secondly, because organic molecules, of which we now know there are a lot in space, have emission bands in the millimeter wave region. And if you can do spectroscopy, you can measure motions because you can do Doppler. Okay, so these are fantastically accurately constructed dishes. At the bottom left there, what you can actually see is the surface of these is active. there are elements which continuously deform the surface to ensure that it's an absolutely perfect parabola, even if the dish is tilted from one side to the other. And all the time the dish is moving, the active elements are changing the structure of the surface. And the real target for this is star formation. What's going on in the middle of these clouds, making stars and planets. This is one image which came from ALMA. What we're looking at here is motions measured in carbon monoxide molecules. And what's thought they happened here is two stars about to form actually collided with each other before they formed. And that's way down in the middle of the Orion Nebula. And the very latest that's appeared, and this is really practically just a few months old, is the image at the top right with the rings. Those are real rings in a disk of matter around the star that's forming, and the gaps in that disk are where planets are actually forming at the moment, and they're clearing a gap in that accretion disk. So ALMA is now starting to study the details, understand the hydrodynamics of the way planets are forming around other stars. Now, if that doesn't blow your mind, I don't know what will. But perhaps this. The microwave background was discovered way back in the 1960s. There's been a whole program of work about understanding the details of the microwave background, because it tells us a lot about early cosmology, way back at redshifts of 1,000. But that leaves us with a big gap. Right on the left, the area of recombination is where we can see the microwave background. At redshifts of about 10, it's where we can see galaxies and some of these exotic extragalactic radio sources. And, you know, this is between the two is where galaxies were forming, and we don't understand how that happens. There are theories, but we can't distinguish between them. And that what's known as the dark age is where the universe consisted almost entirely of neutral hydrogen. So what we want to do is look at a spectral line, which normally is a frequency of 1421 megahertz. And there's a whole industry in looking at the H1 line, studying nearby galaxies and looking at how neutral hydrogen rotates around nearby galaxies. What we want to do here is look at what's going on in that dark age, but because we're now looking at redshifts of 100 or more, that 1421 megahertz has been shifted to much lower frequencies. So in order to study that, first of all, you need an enormous improvement in sensitivity, and you need to work at very low frequencies, which has problems of its own in seeing through the ionosphere. So what's currently being designed at the moment and prototyped is something called the square kilometer array. These are artist impressions, and basically what that's going to be is vast numbers of very cheap aerials connected together by extremely sophisticated electronics and very, very powerful computers. And the amount of data that will get shifted from these aerials is comparable to today's entire internet traffic. So there has to be a very sophisticated hierarchical program of the electronics very near the aerials, filtering information, combining it together, doing some very local calculations, and it's passed in a hierarchical way to local centers, which then get passed to one continental center. And ultimately, some of these aerials are going to be in Africa, and some are going to be scattered all the way around over Australia. And ultimately, there will probably be dedicated fiber optic lines connecting these two parts of the square kilometer array. and the first glimpse of a prototype, the meerkat in South Africa, which is a small prototype version of some of the aerials they're going to replicate in their thousands. And this is looking at the galactic center. And again, the results already are stunning. So what we're anticipating when the full square kilometer array starts to work in possibly 10 years from now is it will have enormous impact. Radio astronomy completely changed the scope of astronomy in the middle of the last century. Everybody believes that the square kilometer array will completely change our view of the universe when it's commissioned in 10 years' time. And that's basically where I'm going to end